Okay, so where is the okay, so we briefly mentioned, I'm just going to do this over so we don't have two this is the first slide anyway. Electric current is the flow of currents from one spot to the other, and we mentioned the fact that 1 ampere is the flow of 6.25 times 10 to the power of 18 electrons per second. We talked also about the fact that if you have an electric car battery, from the positive terminal to the negative terminal there are electric field lines, and if you were to connect a wire from one to the other, electrons would travel along the wire, and that was an electric current. We also said do not do this experiment at home because you'd blow up the battery and probably yourself in the process. Then we talked about the drunkard's walk, right? So the idea that the drunkard's walk is actually a mathematical representation of a random walk. It's also called a random walk, where there's no directional bias. Even though the drunk knows that home is there, any drunk apart from Paul wanders around, right, and ends up at 7 in the morning like drunk somewhere in the gutter near the bar, as opposed to being home, right? Now, an example of a biased drunkard's walk is a situation where now the bar is up on a hill and home is down the bottom of the hill. The drunk is still heading in this general direction, but there's a general bias. Gravity is helping him or her in the general direction of home. Doesn't mean that he makes it home, but he gets somewhere along the way towards home, right? So that's a biased drunkard's walk. So in the application of a bias here, so you've got a wire and you're applying a potential or a bias which is driving, the electric field is pushing the electron in a particular direction. What happens is, instead of a pure drunkard's walk, which ends up having the electron roughly where it started, you end up with a biased walk. That is, the solid lines are the pure drunkard's walk, where the electron zips, hits an atom, zips, hits an atom, zips, hits an atom, and is bouncing around, right? But in the presence of an electric bias, now all of a sudden you have tilted the landscape. So the bar is on top of the hill or the mountain, the home is at the bottom. And so now what's happening is the electron is tending downwards. So in this case, this is up and this is down. So you can see that the dashed trajectory is shifted a little bit in this direction. So instead of ending up here, starting from there, the electron now ends up here. This contributes to something called a drift velocity of the electrons, which is what contributes to the current. The electrons generally drift in the direction of the potential, the bias that's applied. It is. There are two components to it. There's a bias component and a random component. The random component is generally around the direction of the bar. The bias component is in the direction of the slope, in the direction in which gravity is dragging the person, right? The key thing here is, except, okay, this is way beyond the level of this class, except that some kinds of devices that I've worked with in the past called ballistic devices. An electron in a ballistic semiconductor device, the device is so small that the dimension of the device is smaller than something called the mean free path of the electron. The mean free path is the average distance that the electron is able to traverse before hitting an atom. So in a ballistic device, what happens is the electron goes like this instead of bouncing around. But the problem is that the electron interacts with so many atoms on its way that it bounces off the atoms and goes in different directions in any typical material, right? And that's what contributes to resistance. Your question, then yours, Mademoiselle?
I guess that pattern, it's the exact same as the other one.
Yes.
It wouldn't be that. It just would end up further down.
Yes, so this is just shifted.
The bias.
Yeah.
But the ding, 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 ding.
It's more or less the same. Yes. It's more or less the same, except it just shifted a little bit because of the bias. Mademoiselle?
So it would be the same then. Because I think it's interesting because in almost everything in physics that seems random, it ends up not being random at all. And so I'm wondering why this can be random.
The drunkard's walk is random. The biased drunkard's walk has a bias in a particular direction.
Right, but so there's no... So if you did that twice, though, would it still go on that same path, or would it be two totally different paths?
Excellent question. The answer is it would not be exactly the same path for a couple of reasons. One, okay, this is moving into philosophy. One is because we do not live in a deterministic universe. In a purely Newtonian, mechanistic, deterministic universe, you do that same experiment the same, and what would happen is you'd end up with exactly the same path, exactly the same trajectory. But all of the science that we see indicates that we do not live in a deterministic universe. A deterministic universe is like a clock. You wind up a clock, and the clock travels down a certain path. and you don't have any other choice but travel down that path. However, there's a lot of evidence from real life that there is such a thing as agency, free will. You absolutely cannot have free will in a deterministic universe. So there's a huge amount of evidence that we do have free will, which is a strong indication we do not live in a deterministic universe. A lot of indication that free will is not an illusion, that it's very real, right? In addition to free will, there is also things like consciousness. Consciousness cannot exist in a deterministic universe. And also quantum mechanics. There's a lot of evidence from the physics of quantum mechanics that we do not live in a deterministic universe. So like in quantum mechanics, so some of these interactions are quantum mechanical. So it moves into the realm where you throw a ball against this object, and one time it bounces this way, you throw it against this object in exactly the same way, the other time it bounces that way. It's just like if I were to ask you, would you like a Snickers bar? What's your favorite candy?
I don't have one.
What is your favorite drink? Pepsi, right? So if I were to ask you now, do you want a Pepsi? You might say yes. Mm-hmm. If I were to ask you 15 minutes from now, do you want a Pepsi? You might say yes.
Right.
If I ask 15 minutes after that, you might say no.
Right.
Tomorrow, same time, all the conditions are the same. I ask you, do you want a Pepsi? And you say no. Right? That's an indication of free will. Similarly, with quantum mechanics, you can do exactly the same experiment a second time and not get the same result. Because there is a fundamental indeterminacy at the base, the foundation of the universe. Now, from a philosophical perspective, the reason why we need such a universe is in order to preserve free will. If you did not have such a universe, you could not have free will. So if you wanted to have free will, you have to have such an indeterministic universe, which is an interesting scientific confirmation of the fact that from philosophical reasons we do need to have free will, for whatever that's worth, right? But that's philosophy. But philosophy helps us to understand some of the whys of science, right? Okay, but excellent question, extra credit. Okay, so introducing the concept of a circuit, right? So an electric circuit, here's a battery, wire from the battery to the bulb, wire from the bulb to the battery. What happens is electrons travel from here along the wire to the bulb, through that back to the battery, right? So that completes the circuit. The electrons moving through the filament, which is a thin wire, typically of tungsten, in the bulb, causes resistance because the electrons are hitting the atoms start vibrating, they get excited enough to start saying ouch. When they say ouch, enough of them say ouch, you get different colors. Some say ouch, some say ouch, some say ouch. So all these different frequencies, right, they add up to give you white light, right? Red through purple, blue, and so forth, give you white light. So a representation of this is like this, where the resistor associated with the light is the squiggly line here. You got a switch. In this case, there isn't a switch, but if you had a switch that you can put on and off, and here's the battery. So the voltage source is the battery. When you close the switch, electrons travel from here to the switch, through the switch, up along the resistor and back here, right? Now, an analog to this in terms of water is a hydraulic circuit. Like if you think of a fish tank, right? So some of you may have had fish tanks as kids where you have a little pump that circulates the water, right? Or sometimes you've got the standing water fountains. You can buy a little fountain that you stick in, like it's battery operated or whatever, in your room. And what happens is the water gets pumped around in a circuit. It goes up through the fountain, comes down, right? So in a situation like that, the pump is acting like the battery. The pump is pumping the water up to a higher potential energy into the top here. That water flows down here, down to the pump, and in a circuit. So here's a representation. You got a squiggly line. Like so, any of you who have installed a sprinkler system or played with the sprinkler system, right? So the sprinkler system, you got the wide bore pipes, and then you have the thin, right, very thin tubes that come off of that you actually take to the plants. The thin tubes could be like this. They have a higher resistance to the water flow compared to the big bore pipes. You got a valve you can open and close, and you got a pump or the water supply coming from the city, right, that goes around here. This is analogous in terms of hydraulic circuits. This is analogous to the electric circuit that we just talked about here. In this case, we've got electrons flowing through. In this case, we've got water molecules flowing through, right? Potential difference, which is the same as voltage difference, is the difference in electric potential between 2 points measured in volts. It can be compared to the difference in water pressure between 2 containers of water. So here, there's a difference in water pressure. The pressure here is higher than the pressure here, if you will, to a first approximation, if it's purely due to the height difference. So there's a lower pressure here than here, and that's what causes the water to flow from here to here. In the case of a battery, the battery creates a higher pressure on the other side for the electrons that pushes the electrons through the circuit. Okay, introducing the concept of electrical resistance. Electrical resistance occurs because the electrons are traveling through the wire and they bounce off of the atoms. If you've got more bouncing, there's more resistance. Less bouncing, there's less resistance, right? So here, for instance, hope this never happens to you, but if your house catches on fire, you want a fireman to come to your house and use one of these really big hoses, right? You don't want to be using like a garden hose to try to put off the fire. Why? Way more water comes out of the big fireman's hose, right? Because of the fact that the hose is much broader diameter, so there's less resistance to the flow of the water. Whereas a garden hose has much higher resistance because it's got a small bore. So electrical resistance is the property of the material that resists the flow of the electrical current, and it's measured in ohms. This little hat symbol is the Greek letter for, it's omega, right? Which is used to represent the ohms, which represents the electrical resistance. A superconductor is along the lines of what Brittany mentioned. It's a material where the electrical resistance of the material drops to pretty close to zero. To a first approximation, it drops to zero under special circumstances, including low temperatures. So in a situation like this, if this becomes a superconductor, there's no resistance to the motion of electrons. You apply voltage, it just zips across, right? In most electrical circuits, you have some voltage loss due to electrical resistance. And so the lower the electrical resistance, the more power, electrical power, you're able to transfer without losing power. So here, it's an illustration of a circuit board that has resistors. So these little these things that have these painted lines on them, these little units, these are resistors. So current can come in here. It experiences the resistor, the resistance, and it goes out here. So the higher the resistance, the lower the current that goes through for a given voltage. What these different colors mean, it's just a way of reading. It was a way in the past for people to read the value of the resistor, right? Each of these bands, each color meant a number, like 1, 2, 3, 10, whatever. So you could read this and tell how many ohms or kilo ohms or whatever this resistor was. Cool? Current in general is equal to voltage. Voltage is like the pressure that's trying to push, right? So voltage is like the pressure that's trying to push the current forward. Resistance is like the pressure that's, not really, but it's like the pressure that's trying to push backward. So the greater the forward pressure, the greater the voltage, that means the greater the current. The greater the backward pressure, to first approximation, the greater the resistance, the lower the current. So current is voltage divided by resistance. Okay? So Ohm's law basically states that the current is equal to the voltage divided by the resistance. That's all Ohm's law is. If I increase the voltage, the current goes up. If I decrease the resistance, current goes up. So potential difference of 1 volt across the resistance of 1 ohm will give us a current of 1 ampere. So 1 volt divided by 1 ohm, 1 by 1 gives me 1 ampere. That's the definition of ampere. Okay, introducing the concept of direct versus alternating current. So if you plot current on the y-axis versus time on the x-axis, a direct current is a constant steady flow of electrons, right? So it's like if I'm an electron, I just keep on traveling in this direction, and that is a direct current. An alternating current, what happens is I travel in this direction for a while, then I change my mind and I travel in the opposite direction. I move back, right? And then after a while, I change my mind and I move back. So literally this is what the electrons are doing, right? They walk in this direction, then they walk in this direction, and they keep changing their mind and they oscillate back and forth. That's an alternating current. If you plot this, current on the y-axis versus time, here's the current. Positive current upwards, increasing, comes down to 0, then becomes negative, goes up to 0, then positive, down to 0, negative, and so on, right? Alternating current back and forth. Now a diode, introducing a diode. The diode is a little unit. It's an electrical device that changes alternating current into direct current. So if I have a current that's moving back and forth in this wire, and if I put a diode there, the diode would allow the current to travel only in one direction. So it may allow the current to travel in this direction. When I try to push the current back, it says no, stop. It's like a one-way street, downtown Phoenix, right? Right, so you know the one way versus two ways, right? So the diode ensures that the traffic is traveling in one direction here, and over here you can reverse the diode and it travels in the opposite direction, as opposed to a two-way road that the electrons can travel in both directions. So what the diode does to this alternating current, remember that this is a positive current, that's a negative current, positive, negative. So you've got the sinusoidal variation in the current. The diode clips, it removes the bottom so that now you only have the positive pulses. You can smooth these pulses so that instead of getting the dash pulses, you now get this kind of wavy motion, and you can do things to make it even better. And this is what happens when we get alternating current. The current that's coming out of the plug point is alternating. It oscillates back and forth. You put it into a battery eliminator, right, or a direct current transformer, whatever you want to call it, for one of your, like a computer or something, right? If you need it DC, what happens is there's electronics that takes this signal, cuts off the bottom, right, or flips the bottom, and then you get a thing with a series of pulses, and then you can smooth this to give you a close to direct current. So the diode converts alternating current into direct current. So direct current is charges that are traveling in one direction only. Alternating current is the charges keep changing direction, forward, backward, forward, backward. Introducing the concept of a series circuit. A series circuit is where you put your devices in series. So here is a battery, here's a switch, wire connected, connects to the first bulb, second bulb, third bulb. So an electron that leaves here goes through this wire, and when you close the switch, through this wire, to this battery first, through the second battery, third battery, and back to the battery. Did I say batteries? They should be bulbs. Thank you. Right? So through the first bulb, the second bulb, and the third bulb, and back to the battery. So this is series because the electron, a single electron, travels through the first bulb, then in series through the second bulb, and then sequentially in series through the third bulb. The electron sees every one of the bulbs before it gets back to the battery. In this case, so here's a schematic. Here's the bulbs, here's the battery, here's the switch. You close the battery, the electrons, rather the switch, the electrons travel from the battery through each of the bulbs and come back here. The resistance, remember the resistance is kind of like the backward push, right? The resistance to motion of the electrons of these batteries adds up. So the equivalent, and bulbs, thank you, extra credit. It's like one of those things where a wrong word gets stuck in your head and then it keeps coming out. So the first bulb plus the second bulb plus the third bulb is the total. So our EQ stands for equivalent. The equivalent resistance is equal to resistance of bulb 1 plus resistance of bulb 2 plus resistance of bulb 3, right? So the more bulbs I have, the greater the resistance, which means the dimmer the overall light. Is that a question, sir?
Well, so we have that completed circuit and everything.
Michael, right?
Yeah.
Okay, go ahead.
And so we have that completed circuit. And so essentially, wouldn't it essentially be feeding itself? Like once it goes through everything, and then it goes back in. Essentially, a battery. I mean, theoretically, a battery shouldn't go out because it keeps cycling to itself. But then why? I guess it loses electrons along the way. Is that why batteries go dead? Because it's essentially just circulating.
Like the one we just saw at the beginning of this lecture, right?
Yeah.
Okay, you're right that an electron that starts here will get pushed by the battery all the way through the circuit, back into the battery. It comes through to a first approximation, comes through the battery and back, and so the same electron in principle can circulate again and again. Doesn't necessarily happen in practice. But to answer your question, the reason why the battery loses energy after a while is because what's happening here, the battery converts chemical energy into electrical energy. That's the mechanism. So you have electrodes, 2 electrodes with an electrolyte. So there's a chemical reaction happening in each of those electrodes. That's what is creating. So some chemical is getting used up. It's getting converted into another chemical, and after a while, this gets used up, right? It's kind of a couple of illustrations of this. First, think of us, our human bodies, right? We have a little battery that's all through our system called ATP, adenosine triphosphate, right? What happens is when you use up, right, you break the bonds and use up one of the energies in one of the bonds, the phosphate bonds, the ATP converts into ADP, adenosine diphosphate. So the battery gets discharged, and now you have a discharged battery. So the ADP is just sitting around, you can't use it anymore to a first approximation, right? So you've used up the energy and you like to move my arm or something, right? So you go and do a whole bunch of stuff at the gym, you come back, you're really tired, right? And you feel like totally drained. Like if you don't eat for a week, how do you feel? Like totally weak, right? Different week. And so what's happened is you kind of used up all the ATP.
Okay.
So you need more ADP. So what you have to do is you have to go and eat some sugar, carbs, whatever, right? Protein. And that recharges. So there's chemistry inside you. There are factories and stuff like that. They take the energy from the carbs, break those bonds, take that energy and put it into taking ADP and switching it up to ATP. Just like these batteries I'm using in this DVR. Like when I remember, I take these batteries and put them into a charger and charge them up. When I forget, the battery dies halfway through the lecture.
Okay.
Right?
So then with a with a rechargeable battery,
Okay.
what exactly? How is it
In a-
charged?
In a rechargeable battery, what's happening? May I use your Pepsi as an example? Okay. Let's say this is one electrode. And for this electrode to have its chemical power, it needs to have its Pepsi here. Now what happens is when I'm discharging the battery, I'm moving this Pepsi from a high energy state to a middle energy state and then the low energy state. Once the chemical reaction has moved to this end, what happens is there's no more energy. Once all of the Pepsi bottles that she has that I gave you like every 15 minutes, right? Once all of it is transferred over here, there's no more Pepsi available. It's all gone. He drinks them all off, right? So what happens is, that's it. It's done. So that's a normal battery. Now in a rechargeable battery, the design of the process is I can send current in the opposite direction, which you can't typically in a regular battery. And that takes this empty Pepsi bottle, fills it up with Pepsi and moves it here, and then moves it here. So you end up with a whole bunch of charged up Pepsi bottles. So that's what happened in rechargeable. Now, over time, after 1,000 charges or something, the rechargeable battery dies, and what happens is some fraction of these get broken on the way. So you can't do that anymore. Extra credit, mademoiselle?
Okay, well, so if none of that energy or electricity is reused, coming back into the battery, then why does it need to be connected on the other end?
To a first approximation, it is reused.
Okay.
In this particular case, to a first approximation. Remember that I talked about onions, levels, all that kind of stuff? At the basic level of physics, an electron that's sent from here goes all the way through here, comes back, then gets sent here, so it's reused. In reality, what happens is that, like for instance, power coming from the wall, in principle, you don't have to connect, you don't have to have a return path back into the wall. This is what happens, unfortunately, if you stick your finger in the socket. Instead of providing a path back to the wall, now the electrons come through your finger, through you, and go to the earth. Right? But in that case, this is like an infinite supply to a first approximation of electrons, which is not the case with a battery. Now, you can discharge a battery. Like if you short it, it'll totally heat up and discharge. Now, don't do this in the lab, but on occasion I've had students do it. Right? The battery will get like totally hot, and it may destroy the battery if you just short the two ends. And if you do that with a car battery, it'll probably blow up. Right?
How quick would the car battery blow up?
I'm sorry?
How long would it take the car battery?
I think it depends on the design of the car battery.
I don't think that.
Yeah, it may be that now due to safety.
They would melt and short the plates prior to actually blowing it.
Okay, so it looks like we have somebody here who has experience with trying to blow up his car battery, and and it didn't work. Extra credit to both of you speaking up, right? In principle, it could blow up. I'd rather be safe than sorry, right? We may just have a nice, very beautiful molten mess.
So with this series circuit, this is like with Christmas lights. So if one of those
Yes.
bulbs is broken, it can't go to the next light.
Good point. So in the old Christmas sets, that's what happened. All of them are in sequence. But the newer sets have recognized this to be a problem. So what they do is they have segments that are in series in parallel with other segments. So if one bulb dies, you lose a segment, not the whole string, right?
And then you don't know which one it is.
Yeah, so I mean, it used to be a huge pain in the past where you have to one by one take out all of these bulbs and replace them, right? Okay, so that's a series circuit. I'm sorry?
They have these little tester things now that you
They're
plug in there.
so
You
cool.
pump them.
Yeah.
They work really well, but all they're doing basically is generating voltage and feeding it back the other way. So it's just-
Okay, so you can tell which, like where. Okay, pretty cool. Extra credit. Okay, moving on then to a parallel circuit. A parallel circuit is where the electron paths are parallel. So here it got an electron traveling from here to here. When it gets here, the electron has to decide which bulb to go through. It can go through the first bulb, or the second bulb, or the third bulb. But it'll go through only one of the bulbs. In the series circuit, the electron travels through each of the bulbs sequentially, one after the other, before it gets to the battery. In this case, the electron goes here and says, hey, I like the middle bulb, the middle path. So it goes through the middle bulb and comes to the battery without having seen either of the other bulbs. So for that particular given electron, it is as if these two bulbs do not exist at all. Another electron can come over here and decide, hey, I like the upper path. So it goes up to the upper path, right? And it ignores these. And a third electron may come along and say, hey, I like the lower path. And it goes down along the lower bulb, then comes back.
Is that random?
to a first approximation that is random. Yes, another one of those processes, right? We have no way of predicting. If you take an electron and label it, put a little sticky on it, say, hey, I'm electron A, and send it down the path. First of all, you'll get a Nobel Prize if you're able to do it, right? Guaranteed. And even more important than the Nobel Prize, you get an automatic A in this class, right? No more tests to be taken. So this weekend, come up with a way of labeling an electron, right? And guaranteed Nobel Prize and A in the class, right? So, but if you were to label it and send it through the circuit, there's no way to predict which of those three paths it's going to take. A second Nobel Prize to you if you come up with a way of predicting it, right? So, in the schematic here, electron comes from the battery, travels along here, takes one of these paths. In this case, through this path, light bulb, the bulb lights. This path, bulb lights. In this case, the switch is open, so no current travels here and the bulb is off. So in this case, you can see this bulb is on, that is on, and this one is off. Now, in this case, this is called the harmonic mean, right? You know, in school you've heard of a mean and a median and the mode, yes? You all know about arithmetic averages, right? Like, so if I were to say the average wealth of this class is, and I take your wealth is like $80,000, your wealth is $150,000, your wealth, I don't mean to diss you, is $30,000, and so on, right? So I take all of this wealth, I add it up, and then we take the average, we divide by the number of students. That's the arithmetic mean. The geometric mean, now you can do that with weight, you can do that with height, you can do that with anything, right? Now the geometric mean is you take your whatever number, right, multiply by your number, multiply by your number, multiply by your number, and so on. Multiply instead of add, then take the nth root. So if there are, 20 students in the class, you would multiply all of your wealths or heights or weights or whatever, and then take the 20th root. That's the geometric mean. So arithmetic mean, geometric mean. The harmonic mean is where you take the reciprocal. You add up all the reciprocal. You all know what a reciprocal, right? Like, if we say that your wealth is $30,000, the reciprocal is 1 over 30,000. So we take 1 over your wealth, 1 over your wealth, 1 over your wealth, add it all up, summation of all the reciprocals of your wealths, and that will be equal to 1 over the average harmonic mean. So that happens with resistances. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Where each of these is the resistance of one of these bulbs. Now, students will sometimes make a mistake. 1 over R1 plus 1 over R2 plus 1 over R3 is not equal to 1 divided by the sum of R1, R2, R3. That's not the same thing. Right? So you have to take the reciprocals first before you add them up. So that's the formula. And what happens is, so the equivalent resistance of a parallel circuit is lower than the series circuit. It's even lower than that of a single bulb, right? It's like driving down a multi-lane highway. It's faster in terms of the travel of the traffic than down a single lane country road. At your home, typically what happens is all of your electrical appliances are hooked up in this kind of a fashion where you have your lamp drawing 2 amps from the lines coming to your home. The power company is supplying you 20 amps at 120 volts. Here's a fuse. So the electrons travel here. Some of them go through the lamp, some of them continue on, then go through your heater, some of them continue on and go through your toaster, and so on. So notice that each of these is in parallel in your house. You do not want to hook them up in series. Why not? If you hook up all of your stuff in series, all you have to do is put off any one switch in your house and everything goes off. Wouldn't that be funny? If any one light in your house is off, right? Or if your toaster dies. Toaster died, no more power, nothing works, refrigerator's off, right? And you have no clue what the problem is. You have to go around and do your little power thingy on each one. So that's why it's all in parallel. Okay, so introducing the concept of electric power. We talked about earlier, power was work done per unit time, right? So power is the energy transfer, the rate of doing work. And for electricity, power is equal to the current multiplied by the voltage. So if you have 110 volts coming out of here, and you got 1 amp coming out of it, you multiply 1 amp multiplied by the 110 volts from the power supply, and that gives me 110 watts. So power is measured in watts or kilowatts, where a kilowatt is equal to 1,000 watts. And 1 ampere multiplied by 1 volt gives me 1 watt. So if you look at incandescent light bulbs, at the top typically the power would be stamped. You'd see a thing that says 100 watts, 100 W for watts, and 120 volts, right? So that tells you what the power is that's being drawn for that particular voltage. And if you open up one of these bulbs, don't do it. You'll see something like this. We have a metal wire connected down here, which is one of the contacts, going up like this. Another thick metal wire connected to the threads, the metal of the threads going here, and then you